This is Algebra 2, calling it test number 3 since we're on week 3. Spring test number 3. We got through lesson 7.2 where we did radicals. We did properties of rational exponents. We are changing the first 3 problems and omitting number 4 and 5 on the study guide I handed out. You had the 4th root of 6 times the 4th root of negative 6. We are changing that to the 4th root of 8 times the 4th root of 2. When you have the same root like this, both of them being 4, and multiply the radicand, the thing that's under the radical. So what that gives you is the same 4th root. 8 times 2 is 16. So it's just asking you, what is the 4th root of the number 16? I gave all of y'all a chart of exponents. Just go look at the top where you had that caret 4 and look down till you get to the number 16. Look off to the left and you see the number 2. Or you know that the number 2, when you multiply it by itself 4 times, is 16. Remember, this is an even exponent, so not only is it the number 2, it's going to be a positive and a negative 2 for that one. We changed number 2 and number 3 as well. Number 2 originally said the 3rd root of 108 divided by the 3rd root of 2. Okay, that'll give us, if we had done that, would have given us the 3rd root of 52. Just wanted to make something a little bit simpler for you to work with since these are new. When you have a fraction under a radical like number 3, you can separate it just like you could do with square roots. Remember, anything you can do with square roots, you can do with any other root like cube roots. All the same rules apply. It gives you the 3rd root of 32 over 4. Or you don't even need to separate it, I guess, in this sense. You could say 32 divided by 4, and you can get the 3rd root of 8. So again, it's asking you what number, when you multiply it by itself 3 times, gives you the number 8, and it's 2. Or you can look at your table. Now, unlike number 1, where it was both positive and negative, since this is an odd root, 3, it's only positive 2. For number 3, originally it said the 4th root of 240 divided by the 4th root of 5. Again, we're changing that one. You'll get the 4th root of 5 goes into 24 4 times, into it 48 times. Again, it's not going to give you a perfect 4th root. So I did something that'll give you a perfect 3rd root instead. It's a little bit easier. The 3rd root of 256 divided by the 3rd root of 4 is what I want you to change it to. 256 divided by 4 gives you the 3rd root. That stays the same, the 3rd root of 64. Okay, and then again, the 3rd root of 64, if you look at your table, just go up there where it's the caret says 3, go down to the number 64, and it's the number 4. And again, just like number 2, since this is an odd exponent, it is not both positive and negative, it is just positive. Number 4 and number 5, we are omitting completely. If you wanted to try to do those, though, you would do them the same way. When you divide things like this, you subtract like exponents. So you would do like x to the 27 minus 1. I just don't want you to focus on that one again because you're going to get the cube root of 250. I don't want to, that's not perfect and stuff like that. But that's how you would do those two. From 6 on, though, the rest of it will stay the same, and this is all stuff we can handle. 6 says 14 to the 1/2 times 14 to the 1/2. Anytime you have the same base, 14, you can add the exponents. Or if you look at like number 7, they have the same exponent, so you multiply the bases. So you can get around this one by doing 14, it looks like this, to the 1/2 plus 1/2. Anytime you add exponents, or anytime you add fractions, more specifically, you keep that bottom number the same. So 14, the bottom number stays 2. And you add 1 plus 1, you get 14 to the 2 over 2. And then 14 to the 2 over 2 is the same thing as 14 to the first power, which is simply 14. For number 7, you get 5 to the 1/3 times 5 to the 1/3. Again, same exponent this time. Both of them say 1/3. You can multiply bases right here. 5 times 25, we know is 125. Again, that's something that a number we use plenty when we start dealing with exponents and radicals. And you keep that common base. Now, somebody was asking a question a little while ago, should we add the exponents too? No. You wouldn't be able to multiply the bases if you added the exponents. So you leave it as 1/3, just like we left it just like we left the basis as 14 for number 6. So this says 125 to the 1/3. If you rewrote this in radical form, it'll look like this. 125 will be under the radical. This number here, 3, is the index. That means that's the number that tells you which root you're talking about, 3. So the cube root of 125. That top number, 1, or the numerator, tells you what you raise it to after you do the cube root. Um, a shortcut to this is anytime you see the third root, you know you're talking about the, anytime you see the third power, you know you're talking about the cube root of it. So what number times itself 3 times is 125, and it's the number 5. And again, if you raise 5 to the first power, it simply stays as the number 5. And again, this one is not both positive and negative. This one is only positive 5 since it's an odd exponent. 8 to the 4 over 3, again, same thing. Now you're not doing any multiplying, so you have to write it in radical form. 8 is the number that's going to be under the symbol, or the radicand is going to be 8. The number 3 is the index, so it's the cube root of 8. And the number 4 is going to be what you raise it to after you take the cube root of it. So inside parentheses, you do that first. What number times itself 3 times is the number 8? We know we get the number 2 out of that. And again, it's only positive 2 because it's only one of them since it's an odd exponent 3. 2 is now being raised to the 4th power. So that means 2 times itself 4 times. 2 times 2 is 4, times 2 is 8. We know times 2 is 16. Anything to the 0 power is 1. Number 10, 2 to the negative exponent. Anytime you have a negative exponent, remember the elevator rule applies. If there's a fraction, move it to the other part of the fraction that's not in. If it's at the top, move it to the bottom. Bottom, move it to the top. If there's no fraction, create one by putting it over the only number you're allowed to put everything over without changing it, 1. 2 is being raised to the negative exponent, so it has to go down to the bottom of the fraction. Remember, you need to leave 1 at the top as a placeholder, and now 2 is being raised to the positive 4. Negative becomes positive when it rises the elevator. Again, we just did a minute ago 2 to the 4th power. We know it's 16, so it's 1 over 16, or just multiply 2 times itself 4 times. For number 11, you have 5 over g to the negative 4th, h squared, or h to the 2nd power. The only thing being raised to a negative exponent in this case is g. G is being raised to a negative. Everything else doesn't have to ride the elevator. It stays where it is. So g has to go up. 5 stays on top right where it is. H squared stays on bottom right where it is. G goes up, and it becomes g to the positive 4th. And this is all you can do because you can't subtract 4 minus 2 since they're not the same base as g and h. Number 12, 5.91 to the negative 9th times 5.91 to the 10th. Just like number 1 was, you have the same base, 5.91. So you add the exponents, 5.91, and there's no reason to write this step. I'm just showing you to the negative 9th plus 10. Negative 9 plus 10 is 1. So you have 5.91 to the first power, which is simply 5.91. G to the 10th times 2g. Now that exponent for this one is not shown. The exponent right here, 1. You can't forget that one. There's a 1 also in front of this if you need to see it. So you multiply 1 times 2, these two numbers, and you get the number 2. And the same base is g and g, so you add the exponents 10 plus 1. This will be where you'll make your mistake. You'll think you need to multiply them and just get the number 10. So what you have is 2g to the 11th power. Negative 8k to the 9th times j to the 9th times k to the 4th. Again, same basis. All of those have coefficients of 1 other than the negative 8. So if you need to look at those 1s, you can do that. It's not necessary to write them in, just so you can see them though. So negative 8 times 1 is simply negative 8. Same basis, k and k are multiplying by each other. So you add those exponents, 9 plus 4. J, on the other hand, is not the same base as anything, so it's simply j to the 9th. You leave it just like that. So to finish this one up, you're left with negative 8. K to the 9 plus 4 is k to the 13th. J to the 9th. Notice nothing else changes. '15 says 3q to the 6th to the 4th. There's only one term here, 3q to the 6th, but notice there's two things. One of them is 3, the other one is q to the 6th. So you need to make sure both of them are being raised to the 4th power. Remember, anytime you raise a power to a power, You multiply exponents, unlike when you multiply bases, you add exponents. So what this gives us is 3 to the fourth power, q to the 6 times 4. Again, multiply in that case. So again, you can use your chart if you don't want to do 3 times itself 4 times. Just go to 3 and go over to the fourth power, and you can see that it is 81. 3 times itself 4 times is 81. Q to the 6 times 4 is 6 to the 24th power. Anytime you divide like bases, like D and D for number 16, you subtract exponents. It gives you D to the 3 minus 12, which gives you D to the negative ninth. Again, you cannot leave a negative exponent, so it has to ride the elevator. So when it rides the elevator, it goes down and it becomes 1 over D to the positive ninth. An alternative way to do this, and some of you already might be looking at it this way, anytime you see things on both the top and bottom of a fraction, you combine them or you subtract them and you keep them on the side where the bigger one was. If you take 12 and you subtract 3 from it, you know you get the number 9. 12 is bigger, so leave it at the bottom. Okay, be careful if that bothers you. What I mean by that one for this next one, number 17, says 5 to the 10th over 5 to the 12th. If I subtract 12 minus 10 right here, I get 1 over 5 to the second power because 12 is bigger than 10. So it's on that side. And 1 over 5 to the second power is 1 over 25. Again, if you need to write out the step where you subtract them, you're going to have something that says 5 to the 10 minus 12, which will give you 5 to the negative second, which tells you to ride the elevator. Once it rides the elevator, it becomes this one. So if you can visualize, if you can see that shortcut, great. If you can't, it just takes 5 more seconds. Not a big deal. 18, m to the 12th, n to the negative 6 over m to the 12th, n to the negative 10th. Okay, so be careful once you start having negative exponents with this because you might forget that minus and a negative number tells you to add it. So in this case, your m's, they're the same. M to the 12th minus 14. We know, again, if we subtracted them, we would get the number 2, and it'll be at the bottom since 14 is bigger. But just for the sake of this, we'll get m to the negative 2 to where we don't make a mistake with those negatives in a second. The other one, n to the negative 6 minus a negative 10. Remember, minus a negative tells you to add a positive. When you add a positive, you know you get negative. Again, negative 6 plus 10 is going to be n to the positive fourth. Now you have something that says m to the negative second, n to the positive fourth. So again, you cannot leave a negative exponent. So something's got to ride the elevator, the one with the negative exponent. So m, this one, needs to ride the elevator. It goes down to the bottom. N to the fourth stays on top, and m squared, or n to the second, m to the second power goes to the bottom. Again, you could probably look at that problem and do it much quicker visually in your head. If you can't, then write it down. Again, it doesn't take a long time. 2 over 7p squared. Anytime you have an exponent outside of a radical, you give the exponent to everything inside, not out of a radical, out of a parentheses, you give it to everything inside. So this gets squared, 2 squared. This gets squared, 7 squared, and p gets squared, p squared. So 2 squared is going to be the number 4. 7 squared is going to be the number 49 because 7 times 7 is 49. And p is going to be squared. We can't reduce 4 over 49. There's no number that goes into both of them. So we can leave this fraction just like it is. There's no negative exponents. There's nothing we have to move. Simplifying the difference of these. This is just subtracting polynomials. Remember, you can only add and subtract like terms. So always start with the biggest degree. The biggest degree in this case is the fourth one, this one here. Negative 5x to the fourth minus a negative 7x to the fourth. Again, remember, anytime you have minus in the middle, it's telling you to do the opposite of what's in the second set of parentheses. So negative 5 plus 7 is positive 2x to the fourth. The next biggest degree is only x to the first. It skips the third and it skips the second. It's okay. Negative 7x minus negative 9x. Again, minus a negative means plus a positive. Negative 7 plus 9 is positive 2x. And then finally, the last degree is the constant term with no variable. 5 minus a negative 5. Minus the negative again means plus a positive. 5 plus 5 plus 10. We cannot combine any of those because one of them has x to the fourth, one has x to the first, one has no variable. That's all we can do. Number 21, 8w squared minus 8w minus 8 minus 4w to the squared plus 3w plus 5. If doing it the way we did number 20 was tough for you, relabel it. Keep the first one just like it is, 8w squared minus 8w minus 8. And let this negative or let this minus in the middle change all of the signs in the second one. So 4w becomes negative 4w squared. Positive 3w becomes negative 3w. And negative 5 becomes positive 5. Notice all I did was change the signs. Now you combine them like you would anything else when you're combining like terms. Again, start with your largest degree, 8w squared minus 4w squared. Remember, the sign goes with it. If you need to box it to where you can see it, make sure you keep the sign with it. 8 minus 4 is 4w squared. The next biggest degree is negative 8w to the first power and negative 3w to the first power. Same signs, negative 8 minus 3, add them up. 8 plus 3 is 11. Keep the common sign to make it negative 11w to the first power. And the last thing that you need to do is negative 8 plus 5. Opposite sign, subtract them. 8 minus 5 is 3. 8 is farther from 0. It's negative, so it's negative 3. 4w squared minus 11w minus 3. Okay, number 22, simplifying the sum. So you're not changing signs for these. But again, same thing holds true. To keep it standard form, start with the biggest degree. 6u to the third plus 8u to the third. You can add 6 plus 8 and get 14u to the third. 8u squared plus a negative 5u. Remember, plus a negative just means minus. So 8 minus 5 is a positive 3u squared. Then there's no u to the first power. Oh, I just made a mistake. Look what I just did. 8u squared is the only u squared. There's no u squared on the second one. Don't do what I just did. So since there's only one of them, it'll just be plus 8u squared. Then there is a negative 5u to the first power. That's the next degree. So again, minus 5u to the first power. And then the last thing you have is the constant terms. This one here, 6 plus 2, positive 8. Make sure you check your degrees. You can only combine terms, meaning adding and subtracting them, when they have the exact same variable raised to the exact same exponent. Number 23 says simplify the product. 2 multiplies by everything times this, it's 2. Times this, it's positive 6. And times this, it's positive 8. And n also multiplies by everything. N times n squared, you add n to the 1 plus n to the 2 is n to the third. N times n is, again, 1 plus 1 is 2. And n times that is n. So 2n to the third plus 6n squared plus 8n. And we'll pick up the rest of it on part 2 of the video.